Fractional calculus is a branch of mathematical analysis that studies the possibility of taking real number powers or complex number powers of the differentiation operator and the integration operator J. In this context, the term powers refers to iterative application of a linear operator acting on a function, in some analogy to function composition acting on a variable, e.g., f2 equals f. For example, one may ask the question of meaningfully interpreting as an analog of the functional square root for the differentiation operator, i.e., an expression for some linear operator that when applied twice to any function will have the same effect as differentiation. More generally, one can look at the question of defining the linear functional for real number values of r in such a way that when r takes an integer value, n, the usual power of n-fold differentiation is recovered for n greater than 0, and the minus nth power of j when n less than 0. The motivation behind this extension to the differential operator is that the semigroup of powers dar will form a continuous semigroup with parameter a, inside which the original discrete semigroup of Dn for integer n can be recovered as a subgroup. Continuous semigroups are prevalent in mathematics, and have an interesting theory. Notice here that fraction is then a misnomer for the exponent a. Since it need not be rational, the use of the term fractional calculus is merely conventional. Fractional differential equations are a generalization of differential equations through the application of fractional calculus. Nature of the fractional derivative. An important point is that the fractional derivative at a point x is a local property only when a is an integer. In non-integer cases we cannot say that the fractional derivative at x of a function f depends only on values of f very near x, in the way that integer power derivatives certainly do. Therefore it is expected that the theory involves some sort of boundary conditions, involving information on the function further out. To use a metaphor, the fractional derivative requires some peripheral vision. As far as the existence of such a theory is concerned, the foundations of the subject were laid by Liouville in a paper from 1832. The fractional derivative of a function to order a is often now defined by means of the Fourier or Malin integral transforms. Heuristics. A fairly natural question to ask is whether there exists a linear operator h, or half derivative, such that it turns out that there is such an operator, and indeed for any a greater than 0, there exists an operator p such that, or to put it another way, the definition of dny dxn can be extended to all real values of n. Let f be a function defined for x greater than 0. Form the definite integral from 0 to x. Call this. Repeating this process gives, and this can be extended arbitrarily. The Cauchy formula for repeated integration, namely, leads in a straightforward way to a generalization for real n. Using the gamma function to remove the discrete nature of the factorial function gives us a natural candidate for fractional applications of the integral operator. This is in fact a well-defined operator. It is straightforward to show that the J operator satisfies this relationship is called the semigroup property of fractional differintegral operators. Unfortunately, the comparable process for the derivative operator d is significantly more complex, but it can be shown that d is neither commutative nor additive in general. Fractional derivative of a basic power function. Let us assume that f is a monomial of the form the first derivative is as usual. Repeating this gives the more general result that which, after replacing the factorials with the gamma function, leads us to fn. We obtain the half derivative of the function as repeating this process yields, which is indeed the expected result of for negative integer power k. The gamma function is undefined and we have to use the following relation. For this extension of the above differential operator need not be constrained only to real powers. For example, the th derivative of the th derivative yields the second derivative. Also notice that setting negative values for a yields integrals. For a general function f and 0 less than alpha less than 1, the complete fractional derivative is for arbitrary alpha. Since the gamma function is undefined for arguments whose real part is a negative integer and whose imaginary part is 0, it is necessary to apply the fractional derivative after the integer derivative has been performed. For example, Laplace transform. We can also come at the question via the Laplace transform, noting that in etc. we assert, for example, as expected. Indeed, given the convolution rule and shorthanding p equals x alpha minus 1 for clarity, we find that, which is what Cauchy gave us above. Laplace transforms work on relatively few functions, but they are often useful for solving fractional differential equations. Fractional integrals. Riemann-Liouville fractional integral. The classical form of fractional calculus is given by the Riemann-Liouville integral, which is essentially what has been described above. The theory for periodic functions is the Weyl integral. It is defined on Fourier series, and requires the constant Fourier coefficient to vanish. By contrast, the Grunwald-Letnikov derivative starts with the derivative instead of the integral. Hadamard fractional integral. The Hadamard fractional integral is introduced by J. Hadamard and is given by the following formula. Fractional derivatives. Not like classical Newtonian derivatives, a fractional derivative is defined via a fractional integral. Riemann-Liouville fractional derivative. The corresponding derivative is calculated using Lagrange's rule for differential operators. Computing nth order derivative over the integral of order, the alpha order derivative is obtained. It is important to remark that n is the nearest integer bigger than alpha, i.e. Caputo fractional derivative. There is another option for computing fractional derivatives, the Caputo fractional derivative. It was introduced by M. Caputo in his 1967 paper. In contrast to the Riemann-Liouville fractional derivative, when solving differential equations using Caputo's definition, it is not necessary to define the fractional order initial conditions. Caputo's definition is illustrated as follows. The following list summarizes the fractional derivatives defined in the literature. Other types. Classical fractional derivatives include Grunwald-Letnikov derivative, Sonin-Letnikov derivative, Liouville derivative, Caputo derivative, Hadamard derivative, Marchand derivative, Ries derivative, Ries-Miller derivative, Miller-Ross derivative, Weyl derivative, Erdődy-Kober derivative. New fractional derivatives include Machado derivative, Chen-Machado derivative, Udita derivative, Coimbra derivative, Cato-Gampeller derivative, Caputo-Cato-Gampeller derivative, Hilfer derivative, Davidson derivative, Chen derivative. Review articles. M.D. Ortigueira, J.A. Tenreiro Machado. What is a fractional derivative? Journal of Computational Physics 293-413 UN. Cato-Gampeller. Correction to backquote. What is a fractional derivative? By Ortigueira and Machado. Journal of Computational Physics. Volume 293. The 15th of July 2015. Pages 4 to 13. Special issue on fractional PDEs, submitted for publication in J. Computational Physics v. Tarasov. No violation of the Leibniz rule. No fractional derivative. Communications in Nonlinear Science and Numerical Simulation. Volume 18. Number 11. pp. 2945-2948. Arxiv 1402.7161. Generalizations. Erdődy-Kober operator. The Erdődy-Kober operator is an integral operator introduced by Arthur Erdődy and Hermann Kober and is given by which generalizes the Riemann-Liouville fractional integral and the Weyl integral. Further generalizations. A recent generalization introduced by Udita Cato-Gampeller is the following, which generalizes the Riemann-Liouville fractional integral and the Hadamard fractional integral. It is given by, even though the integral operator in question is a close resemblance of the famous Erdődy-Kober operator, It is not possible to obtain the Hadamard fractional integral as a direct consequence of the Erdődy-Kober operator. Also, there is a Erdődy-type fractional derivative which generalizes the Riemann-Liouville and the Hadamard fractional derivatives. As with the case of fractional integrals, the same is not true for the Erdődy-Kober operator. Functional calculus. In the context of functional analysis, functions f more general than powers are studied in the functional calculus of spectral theory. The theory of pseudo-differential operators also allows one to consider powers of d. The operators arising are examples of singular integral operators, and the generalization of the classical theory to higher dimensions is called the theory of Rie's potentials. So there are a number of contemporary theories available, within which fractional calculus can be discussed. See also Erdődy-Kober operator, important in special function theory. Applications. Fractional conservation of mass is described by Wheatcraft and Mischet. A fractional conservation of mass equation is needed to model fluid flow when the control volume is not large enough compared to the scale of heterogeneity and when the flux within the control volume is nonlinear. In the referenced paper, the fractional conservation of mass equation for fluid flow is groundwater flow problem in 2013-2014. Attingana al. Described some groundwater flow problems using the concept of derivative with fractional order. In these works, the classical Darcy law is generalized by regarding the water flow as a function of a non-integer order derivative of the piezometric head. This generalized law and the law of conservation of mass are then used to derive a new equation for groundwater flow. Fractional advection dispersion equation. This equation has been shown useful for modeling contaminant flow in heterogeneous porous media. Attingana and Killickman extended fractional advection dispersion equation to variable order fractional advection dispersion equation. In their work, the hydrodynamic dispersion equation was generalized using the concept of variational order derivative. The modified equation was numerically solved via the Crank-Nicolson scheme. The stability and convergence of the scheme in this case were presented. The numerical simulations showed that the modified equation is more reliable in predicting the movement of pollution in the deformable aquifers than the constant fractional and integer derivatives time-space fractional diffusion equation. Models anomalous diffusion processes in complex media can be well characterized by using fractional order diffusion equation models. The time derivative term is corresponding to long time heavy tail decay and the spatial derivative for diffusion non-locality. The time-space fractional diffusion governing equation can be written as a simple extension of fractional derivative is the variable order fractional derivative. The alpha, beta are changed into alpha. Its applications in anomalous diffusion modeling can be found in reference. Structural damping models. Fractional derivatives are used to model viscoelastic damping in certain types of materials like polymers. Acoustical wave equations for complex media. The propagation of acoustical waves in complex media, e.g., biological tissue, commonly implies attenuation obeying a frequency power law. This kind of phenomenon may be described using a causal wave equation which incorporates fractional time derivatives. See also and the references therein. Such models are linked to the commonly recognized hypothesis that multiple relaxation phenomena give rise to the attenuation measured in complex media. This link is further described in and in the survey paper, as well as the acoustic attenuation article. See for a recent paper which compares fractional wave equations which model power law attenuation. Fractional Schrödinger equation in quantum theory. The fractional Schrödinger equation, a fundamental equation of fractional quantum mechanics, has the following form, where the solution of the equation is the wave function psi, the quantum mechanical probability amplitude for the particle to have a given position. vector r at any given time t, and h is the reduced Planck constant. The potential energy function V depends on the system. Further, delta equals 2, R2 is the Laplace operator, and mu alpha is a scale constant with physical dimension. Mu alpha equals J1 minus alpha m alpha s minus alpha equals kilogram 1 minus alpha m2 alpha s alpha minus 2. And the operator alpha 2 is the three-dimensional fractional quantum Rees derivative defined by the index alpha in the fractional Schrödinger equation is the Elliott Vy index 1 less than alpha 2. History. In applied mathematics and mathematical analysis, fractional derivative is a derivative of any arbitrary order, real or complex. Even though the term fractional is a misnomer, it has been widely accepted for such a derivative for a long time. The concept of a fractional derivative was coined by the famous mathematician Leibniz in 1695 in his letter to L'Hôpital.